Good morning, everyone, and welcome. I'm delighted to have you here today. We're about to begin a presentation on the Environmental Monitoring Program for Controlled Areas. My name is Dr. S.K. Singh, and I hold a PhD in this field. Over the next few minutes, I'll walk you through the key aspects of this program, including its objectives, methods, and importance. So let's get started and explore how we can effectively monitor and manage environmental safety in controlled zones. Today, we're going to focus on the key objectives for understanding environmental monitoring in pharmaceutical manufacturing. First, we want to grasp the purpose of M and the regulatory basis that guides it. This means understanding why monitoring is essential and how regulations shape our practices. Next, we'll explore the different types of monitoring and sampling methods, so you can recognize which techniques are appropriate in various scenarios. Then, we'll dive into trend analysis, including how to set alert and action limits, and how to perform the necessary calculations. Finally, we'll look at some practical examples and how to interpret the data effectively. All these points connect to our overall goal of ensuring product quality and patient safety through effective environmental monitoring practices. Let's take a look at some typical limits for microbiological environmental monitoring in operation. These are general benchmarks used across many facilities, but it's important to remember that actual site limits can vary depending on specific regulations and the particular environment. When we talk about cleanroom classification, we're essentially categorizing the environment based on how many particles or microorganisms are allowed per volume of air. This helps ensure the environment remains controlled and suitable for manufacturing sensitive products. Understanding these limits is crucial because it helps us maintain product quality and safety. However, always keep in mind that your facility's specific requirements might be different, so it's essential to refer to your site-specific standards and regulations. In the context of overall contamination control, these limits serve as key indicators. They guide us in monitoring, maintaining, and validating our cleanroom environments to meet the necessary standards for microbiological quality. Environmental monitoring, or M, involves the systematic sampling of air, surfaces, and personnel to measure microbial contamination. The goal is to demonstrate that we have control over the cleanroom environment. Think of it as a routine checkup to ensure everything stays within acceptable limits. This program isn't just about microbes. It also includes measuring non-viable particulate contamination in controlled areas. Both microbiological and particulate data help us understand the cleanliness level of the environment. Now, why is this important? Because it's required for both sterile and non-sterile operations. It's essential to protect product quality and ensure we meet good manufacturing practice, or GMP, expectations. By regularly monitoring, we can confirm that our environments, whether sterile or non-sterile, are maintained in a state of control. This helps us support high product quality, safeguard patient safety, and stay compliant with CGMP standards like ISO, USB, and EU GMP. In essence, environmental monitoring is a critical part of our quality assurance system, ensuring everything stays within the proper control parameters for safe and effective products. Let's take a closer look at the different types of sampling we use in environmental monitoring. First, there's active air sampling, which provides us with quantitative results, specifically colony-forming units per cubic meter, or CFU-M3. This method gives us precise data on the microbial load in the air. Then, we have passive air sampling, often using settle plates. While it's more qualitative, it helps us identify trends over time by observing where and how microbes settle. Next, surface sampling involves contact plates and swabs, allowing us to assess contamination directly on surfaces. This is especially useful for pinpointing potential sources of contamination. Additionally, personnel monitoring plays a crucial role. Using glove prints or gown sampling helps us evaluate how personnel might be contributing to microbial presence in the environment. The key point here is that each of these methods contributes valuable data, whether it's spotting trends or detecting excursions. When combined, they give us a comprehensive picture of the environmental microbiological status, which is essential for maintaining a clean and compliant environment. This integrated approach helps us make informed decisions and ensure the integrity of our processes. Now, let's take a look at the personnel sampling points. It's important to sample specific areas of the operator to monitor for potential contamination. We focus on glove fingertips, including all 5 fingers, as well as the forearms and the chest or torso. These areas are critical because they tend to come into direct contact with materials and surfaces during operations. Sampling should be performed at the end of the work shift or just before removing the gown, ensuring we capture any contamination that may have accumulated. This process helps us detect operator-related contamination, which is vital for maintaining a clean environment. Moving on to surface sampling locations, we target key areas that pose a risk to the product or process. These include equipment controls and handles, sterile hoods and counters, material transfer ports, and even the floor or walls near critical zones. The idea here is to select points that truly reflect the risk of contamination to our product or process. By focusing on these areas, we can better identify potential sources of contamination and take appropriate corrective actions. Overall, these sampling points are essential tools in our contamination control strategy, helping us ensure the integrity and safety of our products. Let's talk about the exposure time for settle plates. The recommended maximum exposure in cleanrooms is 4 hours. This duration has been validated because it strikes a good balance. It allows us to effectively capture microbes without risking media desiccation. If the process needs to run longer than 4 hours, it's important to replace the plates with new ones to ensure accurate results. For example, if a process runs for 8 hours, you should set up 2 sets of plates, each exposed for 4 hours. The first set, Plate A, would cover the 0 to 4 hour period, and the second set, Plate B, would cover the 4 to 8 hour period. This way, we can monitor microbial presence over time without compromising the media. Now, moving on to passive air sampling using settle plates. This method relies on the principle that microbes naturally settle out of the air over time. It's especially useful in situations where active sampling might disturb airflow, which could skew results. When placing plates, make sure to position 90mm Petri dishes at locations that represent the risk areas in your cleanroom. Be cautious to avoid turbulent zones, particularly directly under HEPA jets, because airflow can influence where microbes settle and lead to inaccurate readings. Overall, settle plates are a simple yet effective way to monitor microbial contamination passively, provided we place them correctly and adhere to proper exposure times. Now, let's talk about media selection for bacteria and fungi. When we're working with these microbes, we use different types of media to support their growth effectively. For bacteria, common media like tryptic soy agar, or TSA, and soybean casein digest agar, SCDA, are often used because they are versatile and support a wide range of bacterial species. These media are great for general purposes, helping us cultivate bacteria in various environments. On the other hand, fungi, including yeasts and molds, require different conditions. That's where media like saborod dextrose agar, SDA, and malt extract agar, MEA, come into play. These are formulated to favor fungal growth, providing the right nutrients and pH to support their development. You might wonder, why do we need different media? Well, bacteria and fungi have distinct growth requirements, especially regarding temperature and nutrients. Using media tailored to each type ensures we get accurate and efficient growth. Plus, employing dual media allows us to improve environmental surveillance, giving us a clearer picture of the microbial presence in a given setting. So, selecting the right media is crucial for reliable results and effective monitoring. It helps us understand the microbial landscape more thoroughly and ensures we're capturing what we need to see. Now, let's talk about incubation conditions, which are crucial for accurate microbial growth. For bacterial plates, the typical incubation temperature ranges from 30 to 35 degrees Celsius, and the duration is usually between 48 to 72 hours. This provides the optimal environment for bacteria to grow within a reasonable time frame. On the other hand, fungal plates require cooler conditions, usually around 20 to 25 degrees Celsius, and they need more time, about 5 to 7 days, to develop properly. It's also important to note that for organisms that grow slowly, we might need to extend the incubation period beyond these standard times. This ensures we don't miss any slow-growing microbes, which can be critical in diagnostics. Understanding these conditions helps us create the right environment for reliable results, connecting directly to our overall goal of accurate microbial identification. Now, let's talk about how we interpret these results. Essentially, we need to evaluate the data against the site's alert and action limits, as well as observe any trends over time. If we see any exceedances, meaning the results go beyond our predefined thresholds, that should trigger an investigation and the implementation of corrective and preventive actions, or CAPA. Moving on to an example, consider the result summary for coverage of settle plates. Imagine we're working in a grade B cleanroom for 8 hours, and there are 4 locations that are considered high risk. We assign 1 settle plate to each of these 4 locations, so we have 4 plates in total. These plates are exposed for the first 4 hours, then replaced and exposed again for the next 4 hours. So, in total, we end up with 8 plates per day, 4 during the first half and 4 during the second half. This approach ensures we're continuously sampling passively throughout the operation, giving us a comprehensive picture of the environmental conditions over the entire shift. It's a practical way to monitor contamination levels consistently and reliably, and it helps us identify any potential issues early so we can take appropriate action. Let's talk about alert and action limits and what they really mean in our control processes. First, the alert limit is essentially an early warning system. When the counts approach this limit, it signals us to check our controls and review the trend. Next, the action limit is more serious. If we exceed this, it means an investigation is necessary, and corrective and preventive actions, CAPA, must be initiated to address the issue. Now, how do we set these limits? Usually, we base them on historical data, using statistical methods like calculating the mean plus or minus standard deviation, or by referring to regulatory thresholds. When it comes to defining these limits, they depend on how we classify the zones and analyze past trends. For example, in sterile zones, CFU counts per plate in 4 hours can be classified into different grades. For grade A, the limit is less than 1 CFU. For grade B, less than 5. Grade C, less than 50, and grade D, less than 100. So, if counts exceed the alert level, it's time to investigate the trend and see what's happening. But if they go beyond the action level, then immediate corrective actions are required to prevent further issues. This approach helps us maintain control, ensure compliance, and keep our processes in check. Let's walk through a quick example of how we might use statistical alerts and actions with air sample data. Here, we have some historical data points measured in CFU per cubic meter, 4, 5, 6, 5, 4, and 6. First, we calculate the mean, which is simply the average of these values. Adding them up, 4 plus 5 plus 6 plus 5 plus 4 plus 6, gives us 30. Dividing by 6 the number of data points results in a mean of 5. Next, we consider the standard deviation, which measures variability in our data. In this case, it's approximately 0.89. Now, using these numbers, we can set our alert and action thresholds. The alert level is the mean plus 2 times the standard deviation, so 5 plus 1.78, which rounds to about 6.78. We typically round that to 7 CFU. For the action level, we add 3 times the standard deviation, 5 plus 2.67, which is roughly 7.67, and we round that to 8 CFU. This means if our sample exceeds 7 CFU, we trigger an alert, and if it reaches or exceeds 8 CFU, it indicates a need for investigation and corrective actions. This approach helps us respond proactively by identifying when our air quality is approaching or surpassing acceptable limits, ensuring we maintain a safe environment. Now, let's talk about some of the actions we can take through CAPA, or corrective and preventive actions. These actions might include reviewing our cleaning SOPs to ensure they're up-to-date and effective. We might also need to reinforce training for staff, especially if gaps are identified. Additionally, HVAC maintenance is crucial because proper airflow and filtration are key to preventing contamination. Handling excursions and investigations is another important aspect, addressing any deviations quickly and thoroughly. On the other hand, there are immediate actions we need to take when an issue occurs. First, resampling if needed helps confirm whether contamination or deviations are present. Isolating the affected area is critical to prevent the problem from spreading. And of course, investigating the root cause is essential, understanding what led to the issue so we can put measures in place to prevent it from happening again. All of these steps are interconnected and support our overall goal of maintaining a high-quality, compliant, and safe environment. By acting promptly and thoroughly, we ensure the integrity of our processes and product safety. Let's take a closer look at risk assessment and review. First, it's important to perform an annual review of the environmental monitoring program, including alert and action limits. This helps us ensure our control measures remain effective and appropriate over time. Next, we need to conduct risk assessments whenever there are process changes, the introduction of new equipment, or if deviations occur. These assessments help us identify any new risks and adjust our strategies accordingly. Lastly, we should update our sampling plans based on trending data, new information, or changes in regulations. This ongoing review process is essential to maintain a robust and responsive monitoring program that aligns with our overall quality and safety goals. Let's wrap up with some key takeaways and best practices. First, it's crucial to define sampling locations based on a thorough risk assessment. This helps ensure we're focusing on areas that truly matter for quality and safety. Next, I recommend using both active and passive sampling methods. Combining these approaches gives a more comprehensive picture of microbial presence. It's also important to validate settle plate exposure times and media performance. Proper validation ensures the data we collect is accurate and reliable. When choosing media, always opt for bacteria and fungi-specific media, and make sure to use the correct incubation conditions for each. This specificity helps us identify and quantify what we're testing more effectively. Finally, trend your results over time and respond promptly to any excursions or deviations. This proactive approach helps us maintain control and continuous improvement in our processes. Overall, following these best practices will strengthen our sampling program and support our commitment to quality and safety. Let's take a moment to look at some key references that underpin our understanding of environmental controls in cleanrooms. First, ISO 14640-41 is fundamental because it defines how we classify the cleanliness of these environments. It provides the standards for particle counts and helps ensure we maintain the appropriate level of cleanliness for different applications. Next, we have the EU GMP Annex 1, along with WHO and PIC-S guidelines, which set specific limits on viable microorganisms, or CFUs, during operation and sampling. These standards guide us in controlling microbial contamination and help us establish proper sampling procedures to monitor cleanliness effectively. Finally, USB 1116 offers detailed practices for environmental monitoring, including sampling methods and culture techniques. This ensures we have reliable, consistent ways to detect and quantify microbial presence. Altogether, these references form a comprehensive framework that supports safe and compliant cleanroom operations, tying back to our overall goal of maintaining product integrity and patient safety. For further support, please feel free to contact us. We're here to help you with any questions or additional information you might need. Thank you so much for your time and attention today. We appreciate your engagement and look forward to assisting you in your journey.